Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 30-second lecture on trajectory optimization. All right, so let's get started with a video. Now, this is a video of a small RC car that is driving around a racetrack. The inputs for this car are at the bottom, where you can see the steering and the throttle. And the idea is for the robot to optimize these inputs so it can drive around the track as quickly as possible. You'll notice the robot is driving around this track multiple times, and that's because in this video, the robot is using something like reinforcement learning, where it takes what worked and what didn't work, and it uses those past experiences to improve its future behaviors. But overall, I like this video because it shows an example of a new topic that I want to discuss, which is trajectory optimization. At a high level, this RC car is looking for the best trajectory, or the optimal trajectory for driving around this racetrack. And so that's what we're going to discuss in today's lecture. I want to first give a little bit more depth on what are trajectories, and then I'll show you how you can find the optimal trajectory for motion planning problems. Okay, so let's set the stage a little bit with motion planning. The idea is that I'm looking for the right trajectory for my controller to track. So take this example on the left. I've got my robot arm. It's got some start position and a goal position. And what I'm trying to do with motion planning is I want to come up with a path or a trajectory for my robot to use that goes from the start to the goal without colliding it with any obstacles. So here, this is a nice trajectory that I could come up with that moves my robot along this path while avoiding this box over here. Now, in the previous lecture, we introduced motion planning and we discussed an algorithm called the bug algorithm. And this bug algorithm works really well when my robot can only see obstacles that are right next to it. So let's say I've got a drone and I can only see this obstacle that's right next to the drone. That would be a situation where it's appropriate to use the bug algorithm. But now I want to switch gears and think about settings where my robot can see more. Maybe it can see all the different obstacles in its environment. How do I come up with good trajectories when I have access to this information? Okay. So the first thing I need to do is I want to provide a little bit more depth on the way we define trajectories. So we know from the previous lecture that a trajectory xi is just a sequence of waypoints. If I think back to the video at the beginning of this lecture, it's a sequence of steering and throttle inputs I'm going to have for my RC car. Now, each waypoint is a desired position that I want my robot to reach. So you could think about it as a theta d that you're controlling your robot to reach. And we've kind of given each of these waypoints a timestamp so that we understand at this time, this is where the robot should be. So here are some of these timestamps. So I've got a discrete unit of time here. So time 1, time 2, time 3, and so on. And again, this is just telling me the correct sequence for these waypoints. Then theta t, that's going to be the waypoint or the desired position at the corresponding time step. So at time step 1, I want to reach theta 1. At time step 2, I should reach theta 2, and so on. In this specific example with the drone, I'm looking at this system as a plane. I'm just got the XY axis. Z is coming out of the screen towards you. And so these waypoints are just XY positions. Like, hey, here's where I want you to be at the first time step. Here's the correct XYZ position at the second time step, and so on. And so if you just look at a sequence of these waypoints, it's defining a trajectory. And so a trajectory, if you've got K waypoints, you can think about that xi as just a sequence of theta 1 through theta k. And here's what that might look like over here on the right for my specific example. Again, I'm just putting each of these different waypoints in a sequence and making this overall matrix xi. Now, there are a couple ways you might want to write your trajectory, and it's going to depend on the problem that we're trying to solve. The most common way you want to write it is as a matrix. And that's what we just were discussing, where I've got theta 1 through theta k, and each different column is going to correspond to a different waypoint in this trajectory. This is going to end up being an n by k matrix, where n, that's the dimension of my joint space, and k, that's the number of waypoints I have. So an n by k matrix. However, as you'll see later in today's lecture, there are times when I also want to write this trajectory as a vector. And what I can do is I can just stack each of these different waypoints on top of each other. So I'll have theta 1 all the way down through theta k into one very tall vector. Call that xi with a little arrow on the top. This will be an nk by 1 vector, again, because I've got each waypoint has n different dimensions, and I've got k different waypoints that I'm stacking together. Okay, so I've got a trajectory. I can write it as a matrix xi or as a vector with xi with a little arrow at the top. So I know in motion planning, I'm looking for one of these trajectories that moves me from the start to the goal and satisfies my objectives. For example, maybe it's the shortest path or the most efficient path from the start to the goal. So how do I go about finding these optimal trajectories for my robot to track? Well, one state-of-the-art approach is something called trajectory optimization, and that's what I want to focus on in today's lecture. The high-level idea is I'm going to search for a trajectory xi that minimizes a loss function subject to constraints. So again, this is going to be a constrained optimization problem. I've got some loss function, and I want to look for the trajectory that will minimize that loss function subject to some constraints. I actually want to start off by discussing the constraints because those are really intuitive. The idea here is I know that my robot should start off at the start position and it should end at the goal position. And so the constraint I'm going to enforce is that the start position should be the start and the goal position should be the goal. Pretty straightforward. The way I do that is I take my trajectory and I write it in that vector form. So again, I'm just stacking all the waypoints into one long vector, xi with the arrow above it. I'm then going to multiply that by a matrix A, defined on the left, and that multiplication is just going to give me theta 1 and theta 2, the first and the last waypoints along my trajectory. All right, so I've got theta 1, theta k, and the idea is that should be equal to B. And B is just the start position and the goal position. So overall, what I'm saying is that theta 1 should equal theta start. So the first waypoint should be the start. Theta k should equal theta goal. The last waypoint should be the goal. So it's kind of like a long, tedious mathematical way of saying what's really obvious. And this matrix A, it's a large matrix. It's almost all zeros. The only thing that's non-zero is you've got identity on the top left and the bottom right in order to isolate the first and last elements of your trajectory. All right, so that's our constraint, start at the start, end at the goal. Now let's talk a little bit more about our loss function. And the loss function is kind of fun because you can define it as you need for your problem setting. I'm going to show you one example that works in a variety of settings, but you can probably come up with your own loss function based on what you need from your motion planner. But overall, this loss function should encode whatever it is that you're optimizing for. Like, again, in that video at the beginning, we were optimizing for the speed or the total amount of time it took to go around the track. So my loss function would try to capture that mathematically so I can then find the optimal trajectory. Okay, so I've got this loss function L, and I'm just optimizing over my trajectory xi. And down here, I've got one definition that we could use for this loss function. Now, what I'm doing here is I'm summing all the waypoints, starting from the second waypoint to the last waypoint of my trajectory, and I'm summing up across each of these different terms of my loss function. This first term is thinking about the length of my trajectory, and I'm trying to add a penalty based on how long that trajectory is. Specifically, what I'm doing is I'm looking at the distance between subsequent waypoints. So at the beginning, this could be waypoint 1, this could be waypoint 2. I'm thinking about how far apart are these waypoints. And I just sum that across the entire trajectory, think about how far apart all of these different waypoints are. Great, that's the first term. This second term is a little bit more complex, but what it's trying to do is it's trying to give the cost that is associated with a waypoint, theta t, that involves colliding with obstacles. We know that we don't want our robot to collide with obstacles, and so we're going to have a penalty associated with those collisions. So if I expand this is one way you could write that cost function. And again, there are multiple ways you could write this. The advantage of this specific definition is that it's differentiable if you do want to take the derivative of this term. So the cost is going to be defined. I'm going to think about each of these obstacles as a circle. Again, it's a simplification, right? But it's a good starting point. So I'll think about each obstacle as a circle that has a center and a radius. So the center is going to be C. That's going to be the center point of the obstacle. And I'm just going to define a radius around that obstacle. It's like a ball, and I do not want to go inside that ball. So the radius of the ball, that's going to be R. So if my waypoint theta is outside that radius, no cost, right? I'm far away from the obstacle. I don't need to worry about it. The second condition is if my waypoint is within that radius of the center, so it's closer to the obstacle, then I'm going to have a penalty. And that penalty will start off at 0, and it's going to increase the further I move inside that obstacle. And here you can see the definition for that term. It's going to end up being a scalar where I'm looking at 1/2 over the norm of the distance between C and theta minus 1 over R squared. Again, this is one way you can define the cost associated with colliding with obstacles. There are other ways, but the high level idea here is I'm trying to encode the concept that this robot should not run into obstacles in its workspace. Okay, so now I have a loss function, and I know I'm going to want to optimize this loss function subject to constraints. Well, in previous lectures, we introduced one way to do that using gradient descent, and I can apply that same concept here. So the way I'm going to apply this gradient descent is I'm going to start off by defining my trajectory xi. And this will be me initializing with what I think the best trajectory could be. Could be just a straight line from the start to the goal. Maybe I've got a good idea of the initial trajectory. Sure. Call that xi0, and I'm going to initialize xi with that initial guess. The other thing I know is I know where the start and goal position should be. So I'm going to write down for B, hey, make sure you start here and you end here. This is going to define my constraint. Okay, so I've initialized my trajectory and I've said where the start and end need to be. Now I can go through my for loop. And within this for loop, I'm going to be updating my trajectory to try to minimize my loss function subject to the constraint. And then finally, I'm going to return my optimal trajectory at the bottom right here. So let's talk a little bit more about this for loop because that's where the main steps are occurring. And this goes back to what we've discussed previously for gradient descent. First, I'll just compute what is my loss. Then I'll look at a numerical estimate of the gradient. Like if I were to change the different waypoints along my trajectory, how would my loss change? And then I try to move down that gradient. So I'm looking for a new trajectory that has less loss than the previous one, subject to the constraint that we've discussed before. That the start better be the start and the end better be the end. So this is pretty standard gradient descent, but with one little twist, and that's that we have to make sure our constraint is satisfied. If we use this approach, we can end up with some pretty nice trajectories. And here I'm showing you some examples of the outcomes of trajectory optimization. Let me just explain these plots a little bit. At each plot, my robot is starting at position 0, 0, and it's ending at position 1, 1. My robot's just moving in a plane, so again, I'm just moving in the X and Y axes. I start at 0, 0, I end at 1, 1. These circles represent obstacles, so my robot should not go within these circles. The gray line shows my initial trajectory. And for each of these, I just guessed, what about a straight line, right? I had like a pretty naive guess of what the trajectory should be. And then I performed trajectory optimization in order to find these lines that you see in orange. Now, this is what I think would be the optimal path for my robot to follow. It's the shortest path to make sure that I do not collide with obstacles. It also starts at the start and it ends at the end. So I found a feasible motion plan that my robot can then execute in order to solve this task. If you want to try this for yourself, which I encourage you to do so, just download the practice set. You can find it in the description or the pinned comment. I've also got some code that you can use in order to test this out and kind of see how this trajectory optimization plays out for you. Okay, so these are some examples of success. Let's think about some of the pros and cons of trajectory optimization. So it's got several pros. One of them is that you can design the loss function as you see fit. So maybe you've got some other ideas, like I want to make sure this robot stays away from humans. Great. You can add that to your loss function and then optimize it when you're looking for your motion plan. Another advantage is that the optimal path is actually invariant to the number of waypoints. So you can have more or less waypoints and it won't change the shape of this trajectory. So that's also a very nice property to have. There are a couple cons though, and it's important to keep these cons in mind. The first one is that the solution you get is going to depend on your initial guess. And I'm illustrating that over here on the right. So I've got the same general setting where I'm starting at 0, 0. I want to go to 1, 1. And I've got two different initial guesses. Now, these are very bad initial guesses, and that's fine. I just wanted to illustrate the concept. So I've got one initial guess over here, and that leads to a trajectory that goes below the obstacle. I've got another initial guess right here, and that leads to a trajectory that goes above the obstacle. And that just suggests that the initial guess that you make could be pretty important for the answer that you get. And that leads us to our second con, which is that we can get stuck in local minima. Now, if you've seen our previous lectures on gradient descent, you'll remember that that's one of the fundamental issues with gradient descent. Sure, I can use it to optimize and minimize a loss function, but I may not come up with the global optima. I may end up looking at a local minima. And that's what we were seeing over here on the right. My initial guess was a straight path that goes from the start to the goal. My robot has these two obstacles, and it ends up with this path that you see in orange. The robot is basically trying to jump over the obstacles, which we know isn't feasible. The reason the robot thinks this is a good trajectory is because if it locally modifies this trajectory, it's increasing its cost. But we know, if we kind of take a step back, that a trajectory that goes around the obstacles would be better and would have like a global minima cost. So there is a better trajectory, but the robot's just not finding it because it's stuck in a local minima. And this ties back to the first con because the reason this occurred is my initial guess wasn't great. If I'd had an initial guess that, let's say moved slightly through one of these obstacles, the trajectory optimization could refine that. So your choice of your initial trajectory will have a big impact on whether you find a valid solution and maybe even the solution that you get overall. Okay, so in today's lecture, we talked about trajectories, and we also used trajectory optimization to try to find the best trajectory for a given motion planning problem. Like I mentioned, I encourage you to practice this concept with the practice set. The first page has the questions, and the following pages have the solutions. Once you've gone through that practice set and kind of tested out this code for yourself, we're ready to move on to a new topic in motion planning. And this is going to be another paradigm that, again, tries to solve motion planning problems, but just a completely different approach for solving these problems. So I look forward to seeing you there.